Hello, this is yet another calculus video, an integral calculus video on trigonometric substitution. Trigonometric substitution is a handful to say, but it's also a nifty trick to help solve some thorny integrands. How can I integrate that, you think? And you sit there and you stare and you stare, and then you realize, hey, there's that weird thing called trigonometric substitution. This is the second video of 3. In the first video, we talked about using a sine of theta. If you see an integrand with a square root and you've got the components of a squared minus x squared, where a is a constant and x is a variable, you can use a sine of theta. You plug it in for x squared, wherever there's an x, and solve. And it opens up doors, especially inside the square root. It makes it possible for you to actually to integrate. And this is a mystery. It's not really a mystery. It has to do with the secrets of the universe, the relationship between square roots and triangles and such. It's built in. And math, what is math anyway? But math is simply a formulaic way of processing reality. And so square roots are a way of processing the reality of triangles. Anyway, it works, even if we don't understand why. And some people probably do. Euclid maybe did, but he's dead. All right, so if you see a squared plus x squared, again, it doesn't have to be in this order, but if you see a square root of that, then the substitution you're going to do is a tangent of theta. I'm doing 3 videos. The first video is about substituting in a sine of theta. It's already done in this form. This is the second video when you have this particular form, and then you're going to substitute in a tangent of theta. So for example, you look at this and you think, what am I going to do with that? I can't do that. And then you remember, the square root of a squared plus x squared, I can deal with that. So here's an x squared, there's an a square. They're not in the same order, but you can switch it around. There's a property that says you can do that. And so if I substitute a tangent of theta for all the x's, maybe something good will happen. And I have a feeling that the person who made this problem up and used it as an example in the textbook knew what they were doing. So let's try it. We're going to let x equal 2 tangent theta. Remember, a squared is 4, right? So square root of that is x. I'm sorry, the square root of that is a. So 2 is the square root of 4. 2 tangent theta. I'm going to substitute that in for all the x's. Very important step, one that I missed a lot when I was taking a Calculus 2 course at Arizona State this past semester. I had to learn how to do this. Thankfully, I got it down before the test. But what is dx? If you're making this be x, what is dx? Because you have to substitute in for dx as well. You can miss this because you don't substitute in for dx. So if x equals 2 tangent of theta, then dx is going to be 2 secant squared theta d theta, because the derivative of the tangent of x is the secant squared x. That's something you should know. You have to, it's a memorization. Yes, you can look it up, but probably your calculus teachers are going to expect you to know that at some point. So the derivative of the tangent of theta is the secant squared theta. Memorize it. Okay, so let's go ahead and substitute it in. So x squared is 4 tangent squared theta, bam. X squared is 4 tangent squared theta, bam, plus 4. And then, don't forget, I've got to bring the dx along. And there's the dx. All right? That looks awful, doesn't it? But there's a path. It's giving us a path. So again, there's where we ended up. I haven't done anything. I just transferred it to the next page. That's where we ended up on the previous page. Let's cancel some stuff out. So first of all, let's bring this up to the top. Okay, I'm going slow here. Just make it very clear. Oh, I did factor out a 4, right? And I can actually then treat these two parts as 2 different parts. Square root of 4 is 2, so I can make that 8 tangent of theta. I didn't do that. I left it somewhat close. Another identity you should know. Okay, you should know that the derivative of the tangent is a secant squared theta, but you should also know that secant squared theta is tangent squared plus 1. So there's the secant squared right there. I've substituted in. And I've already gone and done the square root of 4. So that's nice, isn't it? Because the square root of the secant squared theta is just secant squared theta. So one of the secant squareds cancels out. The 2 cancels out, right? So the 2's went away. The 4 stayed. Why can't I go 2? One of the secant down here canceled out one of the sequents up here. So we're just left with secant of theta on the top, and then the 4 tangent of theta. So see how it's become a little bit easier to manage now. So where do we go next? Well, I did a little finagling here. Secant is 1 over the cosine, right? And tangent is the sine over the cosine. So if you put secant in square root of cosine and tangent in terms of sine and cosine, it's a little bit flipped, right? Because this tells us about a cosine on the bottom, and this tells us about a sine on the bottom and a cosine on the top. But if you cancel it all out, this is what you end up with. Now we're ready for straight old normal substitution, right? We're going to, I just transferred this from the other side, and I'm sorry that I didn't make it unfold. Try not to look, don't look at the answers. But basically, if I let u equal sine of theta, then I've got in the bottom 4u squared, right? And what's du going to be if I make u sine of theta? Well, the derivative of the sine of x is the cosine of x. Very straightforward. And I've got a cosine, so it works. Whoever made this problem was nice to us. And so I'm left with du, cosine of theta, d theta. There should be a d theta here, I'm sorry. On the top with a 4u squared on the bottom because I substituted that in. Now, this is something I can handle. I went ahead and took the 1/4 out. I went ahead and put it in the form u to the minus 2 because if you have u to a minus power, that's like 1 over u squared. But I personally process it better with it in the numerator. And so what is the integral of u to the minus 2? We're going to go up 1 and put it in the denominator. So if you add 1 to this, it's minus 1, going in the opposite direction. And then I need the minus 1 on the bottom to cancel out. So I always double check. I take whatever I've integrated, and using the fundamental theorem of calculus, I see if I take the derivative of this, does it give me this? So the derivative of this is going to be minus 1 times minus 1, which is going to be plus, which the minuses go away, and that's good because there's no minus here. And then I'm going to subtract 1, u to the minus 2, u to the minus 2. Everything works. And since it's an indefinite integral, I have to add a constant. So let's plug the sine of theta back in for u. 1/4, and then again minus, and the negatives out front, and then minus 1 again means it's in the denominator. So substitute back in sine of theta, and we get, ta-da! This is the integral of what we've been looking for in trigonometric terms. You could also write cosecant, doesn't really matter. Okay, the problem is the problem was in x's, and I'm sorry that it's all shown here. I mean to unfold it to make you see it little by little, but just ignore until we get there. So this is from the previous page. We started with the substitute x equals 2 tangent of theta, right? Which means that the tangent of theta equals x divided by 2, right? Just divided both sides by 2. We've got tangent theta equals x over 2. So if I put a triangle up here, here's the mystery of the universe. The tangent of theta, if this is theta, is going to be x over 2, right? The opposite over the adjacent. And then using Pythagoras, a squared plus b squared equals c squared. X squared plus 4 equals the hypotenuse squared. And if we take the square root, then that's the length of the hypotenuse. All right. So what we have here, we can now find what the sine of theta is. Remember, this is how we ended up with a sine of theta. What is the sine of theta? Well, the sine of theta is the opposite over the hypotenuse, or x over the square root of x squared plus 4 squared. Not x squared plus 4 squared, but x squared plus 4. So that means that the integral, when I put it in these terms, if I substitute this in for sine of theta, it's in the bottom, so it gets flipped, right? 1 over sine theta is going to flip this. So I've got the square root of x squared plus 4 in the top. The x goes down to the bottom, and it was a negative 1/4, so negative 1/4. And so the answer to this problem, using a trigonometric identity of the square root of x squared plus a squared, plug in a tangent theta, is negative square root of x squared over 4 over 4x plus c, quod erat demonstrandum. We've done it. We did this problem using that tricky, fun, crazy trigonometric substitution of a tangent theta.